In the year 1831, William Rowan Hamilton presented on the theory of systems of rays, a profound exploration into the mathematical underpinnings of optical phenomena. Hamilton addressed a significant challenge to the prevailing limitations of geometrical optics in accurately describing phenomena such as caustics and wavefronts. Early 19th century science demanded a more refined theory of light, capable of accommodating its wave-like behavior and the effects of diffraction. Moving beyond the simplified approximations of purely ray-based models, Hamilton's initial endeavor sought to apply his innovative characteristic function method to the complexities of optics, aiming to provide a more comprehensive and accurate description. At the heart of Hamilton's approach lies the characteristic function, a mathematical construct meticulously designed to capture the fundamental relationships between the positions and directions of light rays within an optical system. This function encapsulates the optical path length, a measure of the time light takes to travel between 2 points along a ray's trajectory. Its derivatives reveal crucial information, directly relating to the ray's direction cosines and its spatial coordinates. Mathematically, the characteristic function, often denoted by v, is defined as the integral of the refractive index n along the path of the ray. V equals the integral of n ds, where ds represents an element of the arc length along the ray. The power of this formulation resides in its ability to simplify the analysis of intricate optical systems. Instead of tracking individual rays through multiple surfaces and media, the characteristic function provides a global description of the entire system's optical properties. Hamilton envisioned a unified framework encompassing both geometrical and physical optics. He proposed that wave propagation could arise as a natural consequence of the stationary properties exhibited by the characteristic function. This represented a significant departure from traditional approaches, seeking to bridge the gap between ray optics and the emerging understanding of light as a wave. A specific problem Hamilton targeted was the accurate description of caustics. These are the envelopes formed by light rays, often appearing as bright, focused regions of light. Traditional geometrical optics frequently faltered in predicting the precise shape and intensity distribution of caustics, particularly within complex optical arrangements. Hamilton's method, leveraging the characteristic function, offered a pathway to a more complete and accurate description. By relating caustics to the singularities of the characteristic function, he provided a rigorous mathematical tool for their analysis. Consider a simple lens focusing light as a tangible example. The characteristic function for this system can be derived by calculating the optical path length between an object point and an image point, taking into account the lens's refractive index and curvature. The derivatives of this function then reveal the directions of the rays after passing through the lens. The caustic is determined by locating the points where these rays intersect, corresponding to the singularities of the characteristic function. Hamilton's work drew heavily upon his profound understanding of classical mechanics, particularly the principle of least action. He recognized a deep analogy between the trajectory of a particle governed by minimal action and the path of a light ray, which could be described using similar variational principles. The principle of least action, originally formulated by Maupertuis and later refined by Hamilton, posits that a physical system evolves in a way that minimizes a quantity called the action, the integral of the Lagrangian over time. This idea served as a cornerstone for Hamilton's application of variational methods to the study of optics. The work of Lagrange also exerted a strong influence on Hamilton's development. Lagrange's analytical mechanics, with its focus on generalized coordinates and momenta, provided a powerful framework for describing physical systems in terms of a small set of parameters. This approach resonated with Hamilton's desire to simplify the description of optical systems using the characteristic function. For instance, Lagrange's equations of motion, which state that ddt of dl dq dot minus dl dq equals 0, where L is the Lagrangian, Q represents generalized coordinates, and Q dot represents their time derivatives, bear a conceptual resemblance to the equations Hamilton derived from the characteristic function to describe ray propagation. Hamilton directly acknowledged these influences in his other works, specifically noting the inspiration he drew from Lagrange's methods in his development of Hamiltonian mechanics. Hamilton's work, brilliant though it was, also possessed limitations. The practical computation of the characteristic function for anything beyond the simplest optical system presented a formidable challenge. Calculating the function demanded solving complex differential equations, often without closed-form solutions. Approximations became essential, diminishing the exactness Hamilton envisioned. The computational resources available at the time further constrained its application to systems of limited complexity. Modern computational power has mitigated some of these issues, yet the inherent mathematical difficulties persist when dealing with highly complex optical designs. Moreover, direct experimental confirmation of Hamilton's theory proved elusive in the 1830s. while experiments by Young and Fressel solidified the wave nature of light. Directly measuring the characteristic function represented an entirely different challenge. The technology to trace individual rays with sufficient precision and reconstruct the function did not exist. This lack of direct verification initially relegated Hamilton's approach to a more theoretical domain. Indirect support, however, arrived as the wave theory of light gained acceptance. These difficulties, however, do not diminish Hamilton's contributions. His theory furnished a novel conceptual framework for understanding optical systems. The characteristic function concept, even when approximate, supplied a powerful tool for analyzing and designing lenses and instruments. Subsequent developments in optics, driven by the increasing demands of astronomy and microscopy, built directly upon Hamilton's foundational work. The impact on the theory of systems of rays on subsequent developments in optics and physics has been profound and multifaceted. It formed the bedrock for modern aberration theory. Aberrations are imperfections that arise in optical systems that degrade image quality. Hamilton's framework supplied a means to quantify and minimize these flaws. Later researchers, including Ludwig Philipp von Seidel and Carl Schwarzschild, expanded Hamilton's initial concepts, devising practical methods for calculating and correcting aberrations in complex lens systems. Seidel's work on the 5 primary aberrations, spherical aberration, coma, astigmatism, field curvature, and distortion, directly employed Hamilton's ideas to classify and quantify these defects. Schwarzschild's contributions included methods for designing telescope objectives to minimize aberrations. These built directly from Hamilton's. Furthermore, Hamilton's work exerted a subtle influence on the evolution of wave optics. While his original theory operated within the realm of geometrical optics, ray tracing, his concepts provided a bridge to the more complete wave-based description of light. The characteristic function bears a direct relationship to the eikonal equation, a central equation in wave optics that describes the phase of a wave as it propagates through a medium. The eikonal equation, ds squared dx squared plus ds squared dy squared plus ds squared dz squared equals n squared, where S represents the eikonal and m represents the refractive index, is intimately linked to Hamilton's characteristic function. This connection demonstrated the underlying unity between ray and wave descriptions of light. Hamilton's ideas furthermore influenced Maxwell's development of electromagnetic theory. Maxwell, seeking a mathematical structure to describe the propagation of light as a wave phenomena, discovered in Hamilton's work a valuable model. Hamilton's mathematical methods offered a rigorous framework for describing the behavior of light and paved the way for Maxwell to unify electricity, magnetism, and optics into a single coherent theory. This had far-reaching implications for theoretical physics. Hamilton's legacy extends far beyond optics. His development of Hamiltonian mechanics, an alternative formulation of classical mechanics, provided a powerful framework for understanding the behavior of dynamical systems. Hamiltonian mechanics, with its focus on energy and phase space, has become a cornerstone of modern physics. The Hamiltonian formulation became essential for formulating quantum mechanics. The Schrödinger equation, H bar d psi dt equals 8 half psi, where psi represents the wave function. H bar is the reduced Planck constant, 8 hat is the Hamiltonian operator, relies directly on Hamilton's formula of classical mechanics. Hamilton's contributions to optics and mathematical physics stand as a testament to his intellectual prowess and his profound understanding of the underlying principles governing the physical world. On the theory of systems of rays continues to furnish insights for contemporary research in optics, wave propagation, and mathematical physics. His work continues to inspire new generations of scientists and mathematicians. Its enduring relevance underscores the importance of Hamilton's contributions. His work is a fitting tribute to a mind that profoundly reshaped our understanding of the universe.